Good morning everyone, we're the Curtius team from High School of Saint-Jacques in Liège, and today we're going to present to you our CANSAT project.
In space mission, parts are subjected to high stresses due to high acceleration during the flight. It's important to check that all structural parts can withstand these stresses. This is the aim of our secondary mission, to measure the stresses in the structure of our CANSAT by using strain gauges. Ideally, we had planned to do them to the external cam of the CANSAT, but since it's curved, the gauges would have been pre-stressed and the result would have been very difficult to analyze. Therefore, we decided to place them in the electronic structure.
I'm going to go over the secondary mission's electronic parts in a nutshell. First of all, we have a Wheatstone bridge. It's made up of 4 resistors, one of which is our strain gauge. These configurations allows us to display a potential difference when one of the resistors varies. Since the difference is very small, we added an operational amplifier. We also had to add an offset because we realized that in the event of completion, we would have a negative potential difference that cannot be measured by a microcontroller. So when the parachute opens, the force will be directed upwards, resulting in traction. This first phase is problematic.
So we had no technical skills and we needed to sort advice from various specialists. So we started to meet Mr. Brown at HEPL. He's the director of the science and technology sector, and he helped us with the electronics and the deadline management because he oversaw the OFTI project, so he knew. After we met some engineers in the Safran Aero Booster to learn more about strain gauges. They gave us a little bit of equipment for our secondary mission. And finally, we contacted the Liège Amateur Radio Club, and 2 passionate people came to our school to give us information about antennas, and they lent us one.
After these theoretical aspects, we moved on to manufacture our CANSAT. We started with the parachute, for which we chose a hemispherical shape. We then made the structure, with a metal skirt and complementary parts made using 3D printing. Afterwards, we made the electronics. For the primary mission, the wiring is complete. For the secondary mission, we already have all the components, but we still need to finalize the assembly.
The next step was to enter the testing phase. We first tested the parachute from various heights. The final test was done at Berlitz from a height of 19 meters, and we validated the speed of 7 meters per second. We expect the speed to be faster at higher altitude where air density is lower. We then tested the antenna from a high point to validate the long range. We received data up to a distance of 2,300 meters. We used the antenna test for validating the primary mission. The following data were perfectly transmitted: temperature, pressure, position, acceleration, and simulated strain gauge data.
So another important part of the project was the outreach. So we firstly created an Instagram account where we keep our followers up to date on all of the stages of our CANSAT design, and we also give them some tips. We also held 2 different stands. So firstly, we sold Curtius beers at our school's Christmas market with our logo on them. So our CANSAT name, Curtius, is actually a reference to that typical beer from Liège. We also held another stand, but this time on our school's open days. To finish off, we have displayed every single week a space fact on our school's TV screen to spark an interest in space among the students. So thank you very much for listening to us, and if you have any questions, don't hesitate on asking them.
Right on timing, no time for the questions.
Yes. So you have a very good antenna communication. So what tips did the radio amateurs give you that resulted in such a good communication?
So the people who came to school gave us one of their antennas. So I think that maybe we have good range because we didn't do it all by ourselves, and we don't know really why we have that good communication, but it's a good point. So.
Okay, I have two questions. First, congrats for your job. You confirm that the descent rate is 7 meters per second.
Yes, we tested it, but we are going to retest it for the finals to be sure that it's 7 meters per second. And as we said, we expect it to be higher a little bit when we are higher with our CanSat. And if during another test we saw that it's a little bit lower, we know that we have to stay at 7 meters per second, so we are going to stay at it. And we wanted to stay at 7 meters per second because we were already shocked by the impact of the CanSat when we saw it fall, and we don't want our CanSat to break.
Okay, but the descent rate should be between 8 and 11 meters per second.
Yes, but it was between 8 and 11, but we could also